10.10. The Binomial Series and Applications of Taylor Series. The outline of this video is as follows. We will begin by exploring the binomial series, which is a powerful tool for representing functions of the form, the quantity 1 plus x, raised to a power m. Next, we will apply our knowledge of series to derive the series for the arctangent function, showing how integrating a known series can generate a new one. After that, we will learn how to use Taylor series to evaluate indeterminate forms, providing an alternative method to L'Hopital's rule for certain limits. We will then uncover one of the most remarkable results in mathematics, Euler's identity, which connects the exponential function to trigonometry. Finally, we will conclude by reviewing a table of commonly used Taylor series, which will serve as a valuable reference for future problems. In this section, we will explore how Taylor series provide a powerful method for solving problems that would otherwise be very difficult or even impossible to handle with standard techniques. We will focus on three key applications. First, we will see how to evaluate integrals of functions that do not have elementary antiderivatives. A classic example is the integral of the sine of x squared. While we cannot write down a simple function for its antiderivative, we can express it as a power series and integrate it term by term. Second, Taylor series give us another way to evaluate limits that result in indeterminate forms. And finally, these series allow us to extend the definition of functions, like the exponential function, from the domain of real numbers to the more general domain of complex numbers. To begin our exploration, we will first introduce a particularly useful tool, the binomial series, which is the Taylor series for the function 1 plus x, all raised to the power m. The binomial series is a specific but very important Taylor series that allows us to expand any expression of the form the quantity 1 plus x, all raised to the power of m. This expansion is the Taylor series for this function centered at x equals 0. The series begins with 1 plus m times x plus a term with x squared, and so on. A clear pattern emerges in the coefficients. The coefficient for the term containing x to the power k is a fraction. The numerator is a product of k terms, starting with m and decreasing by 1 at each step, down to the term m minus k plus 1. The denominator is k factorial. Now, consider what happens if m is a non-negative integer. Eventually, one of the terms in the numerator will be m minus m, which is 0. This makes all subsequent coefficients 0, and the infinite series terminates to become a finite polynomial. If m is not a non-negative integer, the series is infinite, and it converges only when the absolute value of x is less than 1. The binomial series provides a powerful way to represent powers and roots as polynomials. Here we have the compact and powerful formula for the binomial series, which generalizes the familiar binomial theorem to work for any real exponent, m. The function, the quantity 1 plus x, raised to the power of m, can be written as 1 plus an infinite sum. The sum runs from k equals 1 to infinity, where each term consists of a special coefficient multiplied by x to the power of k. This coefficient, denoted as m over k in parentheses, is called the generalized binomial coefficient. Let us look at how to calculate this coefficient. For k equals 1, the coefficient is simply m. For k equals 2, it is the fraction m times the quantity m minus 1, all over 2 factorial. The general formula for k greater than or equal to 3 follows this pattern. The numerator is a product of k terms, starting with m and decreasing by 1 at each step, down to the term m minus k plus 1. This entire product is then divided by k factorial. This single formula gives us a systematic way to expand any function of the form 1 plus x to the m into a power series. Let us test our new binomial series formula with a specific case to see if it reproduces a series we already know. We will set the exponent m equal to -1, which corresponds to the function 1 over the quantity 1 plus x. First, we must evaluate the generalized binomial coefficients for this value of m. The coefficient -1 choose k is a fraction. The numerator is the product of k terms, starting with -1 and decreasing. -1 times -2, and so on, down to -k. This product is equal to -1 to the power of k times k factorial. Since the denominator is also k factorial, the entire coefficient simplifies to just -1 to the power of k. Substituting this result back into the general formula gives the series 1 minus x plus x squared minus x cubed, and so on. This is exactly the familiar geometric series, which we know converges when the absolute value of x is less than 1. This example confirms that the binomial series works as expected for this important case. Let us now apply the binomial series to a very common and important case, approximating the square root of 1 plus x. This is equivalent to setting our exponent m equal to 1/2. Plugging m equals 1/2 into the general formula generates the series shown here. The first two terms, 1 plus x over 2, should look familiar. This is the standard linear approximation for the square root function when x is small. The binomial series gives us the terms for higher order approximations as well, such as the quadratic term, -x squared over 8, and the cubic term, +x cubed over 16. This becomes very powerful when we use substitution. For example, to approximate the square root of 1 minus x squared, we simply replace every x in our series with the quantity -x squared. This immediately gives a useful polynomial approximation for a more complicated functions. The main takeaway is that this specific series is a practical tool for approximating functions with square roots. One of the most powerful applications of Taylor series is evaluating integrals that do not have a simple, closed-form solution. These are often called non-elementary integrals. The integral of sine of x squared, for instance, is a famous problem in optics and physics, but its answer cannot be written using standard functions. Our strategy is to replace the function inside the integral with its power series. First, we take the well-known series for sine of x and substitute x squared for x in every term. This gives us a new power series for the function sine of x squared. Now we have an integral of a long polynomial, which is very easy to solve. We can simply integrate this new series one term at a time using the standard power rule. The result is another power series, which represents the antiderivative we were looking for. Notice we must include the constant of integration, c, just as we would for any indefinite integral. By doing this, we have successfully expressed a difficult integral as an infinite series. Now we will use our power series to estimate a definite integral to a specific accuracy. Our goal is to find the value of the integral of sine of x squared from 0 to 1, with an error less than 1/1000th. First, we take the antiderivative series from the previous slide and evaluate it at the upper and lower bounds of 1 and 0. This gives us a numerical series, 1/3 minus 1 over 42 plus 1 over 1320, and so on. Because the signs of the terms alternate, we can apply the alternating series estimation theorem. This powerful theorem states that if we stop our sum at a certain point, the error will be smaller than the absolute value of the very next term in the series. Let us look at the magnitude of the terms. The third term, 1 divided by 1320, is approximately 0.00076. Since this value is less than our required error of 0.001, it is the first term we can leave out. This means we only need the first two terms for our approximation. The integral is approximately 1/3 minus 1 over 42, which equals about 0.310. We can find the power series for the arctangent function by integrating a known series, which is much easier than finding its higher-order derivatives directly. Our starting point is the fact that the derivative of the arctangent of t is the fraction 1 over the quantity 1 plus t squared. We can express this fraction as an infinite geometric series, which is 1 minus t squared plus t to the fourth minus t to the sixth, and so on. Next, we integrate this power series term by term from 0 to x. Integrating 1 gives x. Integrating negative t squared gives negative x cubed over 3. The next term becomes x to the fifth over 5. And this alternating pattern continues. The resulting series, as shown in the summation formula, converges for any x where the absolute value of x is less than or equal to 1. A formal proof confirms this by showing that the remainder term from the integration goes to 0. Thus, we have derived the power series for arctangents not from the Taylor formula, but by integrating a simpler related geometric series. A remarkable application of our series for the inverse tangent is a formula for the number pi. If we substitute the value x equals 1 into the series, the left side becomes the inverse tangent of 1, which we know is pi over 4. This gives us the famous Leibniz formula, where pi over 4 equals the alternating series 1 minus 1/3 plus 1/5 minus 1/7, and so on. While this formula is mathematically beautiful, it is not very practical for computation because the series converges extremely slowly. You would need to add a massive number of terms to get an accurate approximation of pi. A more efficient approach uses trigonometric identities to express pi in terms of inverse tangents of smaller numbers. For example, pi over 4 also equals the sum of the inverse tangent of 1/2 and the inverse tangent of 1/3. Because the arguments 1/2 and 1/3 are much closer to 0, their respective series converge very quickly. This means that for practical calculations, we use the same core series but with smaller inputs for x to ensure rapid convergence. Taylor series provide a powerful alternative method for evaluating limits that result in an indeterminate form, such as 0 divided by 0. Let us examine the limit as x approaches 1 of the fraction with the natural log of x in the numerator and the quantity x minus 1 in the denominator. Our strategy is to replace the function in the numerator, the natural log of x, with its Taylor series expanded around the point the limit is approaching, which is x equals 1. This series is the quantity x minus 1 minus 1/2 times the quantity x minus 1 squared, and so on. After substituting this series into the limit, we can divide every term by the denominator, x minus 1. This simplifies the expression inside the limit to 1 minus 1/2 times the quantity x minus 1, plus other terms that still contain a factor of x minus 1. As x approaches 1, all of these remaining terms go to 0, leaving us with the final answer of 1. By replacing a function with its series, we can often solve difficult limit problems using simple algebra. We can also use Taylor series to solve more complex indeterminate forms, especially when applying L'Hopital's rule multiple times would be cumbersome. Our goal is to evaluate the limit as x approaches 0 of the fraction, with sine x minus tangent x in the numerator and x cubed in the denominator. First, we replace both sine of x and tangent of x with the first few terms of their Maclaurin series. The series for sine x starts with x minus x cubed over 6, while the series for tangent x starts with x plus x cubed over 3. The key step is to subtract these two series. Notice that the linear terms, the single x terms, cancel each other out. The next term is negative x cubed over 6 minus x cubed over 3, which combines to give negative 1/2 times x cubed. Now we can substitute this result back into the limit. The x cubed in the numerator and denominator cancel, leaving negative 1/2 plus some terms that still depend on x. As x approaches 0, these remaining terms disappear. Therefore, combining series expansions allows us to find that the limit is negative 1/2. We can gain a remarkable insight by exploring what happens when we substitute a purely imaginary number into the Taylor series for the exponential function. This step provides a powerful motivation for connecting exponential functions to trigonometry. Let us begin with the familiar series for e to the power of x. We will now formally replace every instance of x with the quantity I times theta, where theta is a real number and I is the imaginary unit, the square root of -1. After substituting, our next step is to simplify the powers of I. Remember that I squared equals -1, I cubed equals -I, and I to the 4th power equals +1. Applying these simplifications allows us to regroup the terms of the series. We can collect all the terms that do not have an I, which form the real part, and all the terms that are multiplied by it, which form the imaginary part. When we do this, we find that the real part is precisely the Taylor series for the cosine of theta, and the imaginary part contains the Taylor series for the sine of theta. We can now formalize the connection between the exponential and trigonometric functions using a relationship called Euler's identity. This identity defines the quantity raised to the power of I times theta as being equal to the cosine of theta plus I times the sine of theta. A major benefit of this is that it allows us to find the exponential of any complex number, say a plus I times b. The exponential e raised to the power a plus ib becomes the product of e to the a and e to the ib. Applying the identity, this simplifies to e to the a multiplied by the quantity cosine of b plus I sine of b. A famous and beautiful consequence arises when we evaluate this identity for theta equals pi. We find that e to the power of I times pi is equal to the cosine of pi plus I times the sine of pi. This evaluates to -1 plus I times 0, or simply -1. Rearranging this gives the equation e to the I pi plus 1 equals 0, a single, profound statement that connects the 5 most important constants in mathematics. This slide presents a table of the most important and frequently used Taylor series expansions. Think of this as your toolbox. These are the fundamental series that we will use as building blocks to analyze more complicated functions. Notice that the series for the exponential e to the power of x, sine of x, and cosine of x are valid for all values of x. This makes them extremely powerful. In contrast, the geometric series, the natural log, and the inverse tangent series are only valid within a specific interval of convergence. It is critical to always be mindful of this interval when using a series. In the upcoming examples, we will not derive series from scratch. Instead, we will start with these known expansions and modify them, for example, by substituting a new expression for x. Becoming familiar with these key series will allow you to solve problems much more efficiently. Let us summarize the key applications of Taylor series we have discussed. First, we introduced the binomial series, which generalizes the expansion of the quantity 1 plus x to the power m. This allows us to handle cases where m is not a positive integer, as long as the absolute value of x is less than 1. We then explored the broader utility of Taylor series as a fundamental tool. We saw how they can be used to approximate complicated functions with simpler polynomials, to integrate functions that lack elementary antiderivatives, and to resolve indeterminate forms when evaluating limits. Finally, We examined Euler's identity, which states that e to the power of I theta equals cosine theta plus I times sine theta. This profound equation connects the exponential and trigonometric functions and is a cornerstone of complex analysis, with wide-ranging applications in physics and engineering. To wrap up, here are a couple of review questions to help you solidify your understanding of how to apply these series. The first question asks you to use the general binomial series formula to find the first few terms for the function f of x equals the quantity 1 minus x squared, all raised to the power of negative 1/2. It then asks you to consider how this series relates to the derivative of the inverse sine of x. This is a great exercise for connecting a general tool to a specific, important function. The second question provides a classic example of using series to evaluate limits. You are asked to explain the steps for finding the limit as x approaches 0 of the fraction, with e to the x minus 1 minus x in the numerator and x squared in the denominator. By substituting the series for the exponential function and simplifying, you can easily find the limit, which you should verify is 1/2. Take a moment to work through these problems. They are an excellent check on the key techniques from this video.